Okay, uh, so in the polar coordinate Laplace differential equation, we at some point had the Euler Lagrange equations, which was like x squared y double prime plus xy prime, and then there was some number here, some constant here, and then y. And then this, although you have a non-constant coefficient for the second order differential equation, we were able to solve this because the order of the polynomials were going down as same as the order of the derivatives. Such a thing was called the Euler Lagrange equations, and in such a case, we know that the solutions look like one looks like they look like x to some power r, and then you plug this in and you can figure out what that was. So that was what we went through in Laplace on the polar coordinate system. However, if we try to solve the wave equation on the disk in polar coordinates, you don't have any luxury of the degree of the polynomials going down like that. Okay, and you end up with something called the Bessel's differential equation. And you can also do something similar on a three-dimensional ball. You can solve wave equations or Laplace differential equation in the ball. And if you do that, you again get a second-order differential equation that's in the form of a Legendre equation. So I'm not going to write down the Bessel's equations yet, but again, those are equations where the coefficients are functions of x. And those are a million times harder than the cases that you learned where the coefficients are constant numbers. Okay. For constants, we know that all the solutions look like e to the sum r times x with some constant r, right? But that's no longer true. So you have to settle for the solution being very complicated, not the usual kind of functions that you're used to. Rather, you just have access to their power series. Okay? Now, you know that sine function, exponential function, all these things have the Taylor series, right? Power series. And I explained why knowing the power series allows you to know their values for different values of x, so it's like knowing it, right? So, although the format of the solution might look very strange because you're trying to write down the solution as a power series that's never ending, right? You can still give meaning to it because you can evaluate it, right? So that's the way we're going to approach such a thing. I'm going to do the Legendre equation first because Bessel's equation has something called a singularity, and although this is a rather more complicated topic where you have to do something called Frobenius method, and it takes like 2 weeks in a regular differential equations course. I'll just limit our discussion to Legendre and Bessel because those are the ones that we need for the PDEs. Okay? All right, so let's try to solve this. This is called the Legendre equation. And L is supposed to be a positive integer. Okay? However, or it can be 0. Okay? 0 or a positive integer. Since trying to solve this in generality is a bit hard, let's just choose a simple number and try to solve for that. Okay? So let's say L is 2. Okay? So let's say we want to solve Legendre differential equation for L equals to 2. In that case, it's 2 times 3. So what is this one? 2 times 3 is 6, right? So we'll try to find the general solution to this equation. Now, as I said, we're trying to find the solution in the form of some power series. So you have some unknown constants, a0 plus a1x plus a2x squared plus something something. And in terms of the sigma notation, this would be, in the sigma notation, it's n going from 0 to infinity of a sub n x to the nth power. Right? If n is equal to 0, you get a0 x to the 0th power. What's x to the 0th power?
1.
Anything to the 0th power is 1, so 1 times a0 would create the very first term, right? And then, since this is like a for loop, if you know Python language or some programming language, it's like a for loop, right? Where n increases by 1 every time the loop goes on. So the next number is 1, so you have a1x to the first power, which is exactly this a1x. The next one would be a2x squared. So that represents this series here. Okay, now let's differentiate both sides, because after all, I'm trying to plug this into here, which requires me to know what y prime is and what y double prime is. So I'm going to calculate y prime and y double prime. Okay, so y double prime would be a0 disappears, constants differentiate to 0, a1x becomes just a1. And then this one becomes 2a2x. Okay, I didn't write the next term here, but what would be the derivative of that one? 3a3x squared, and then plus dot dot dot. All right. So what would that be in terms of sigma notation? Okay, so first of all,
a n minus 1 x e minus 1. No.
Oh, yeah, right. So you don't want to say n minus 1. Let's say n starts from 1 now. Okay. Yeah. Since the very first term went away, we're going to say that n starts from 1 to infinity. Okay, and then what goes in here? N times an. You can see that these two numbers are the same, right? If you call this number as n, you get the same number here. And what's here? N minus 1, right? And this makes sense because you can just look at this and differentiate x to the n. What's the derivative of x to the n? N comes down and you subtract 1, so that's exactly this one, right? So we didn't have to write it like that. We could have gone from here to there directly. Except, if you do that, then it will be unclear why your n starts from 1, not 0. Okay? Why does n start from 1 rather than 0? Because n equals to 0 gave you a constant term which differentiates to 0. It's gone. That's why n starts from 1. Does it make sense? Right? Okay, and then y double prime equal to, if you differentiate a1, it's gone. If you differentiate 2a2x, it's just 2a2. And if you differentiate this, you could write 6, but you want to find a pattern, so you don't want to write 6. You rather want to write it as 2 times 3, a3x. Okay. All right, tell me the next term. What would happen here, and what would the derivative be like?
3 times 4 a4.
That's correct. 3 times 4, a4, x to the squared. Okay. Therefore, the summation would be n starting from 2 to infinity. Okay. And what goes here?
n times n plus 1.
Yeah. Right. No. This is n. We call the subscript. So n, and this would be n minus 1. So it would be n times n minus 1. Sorry, I should really have written out 4 times 3. That will be easier for you to process it, right? I should have written down that this one is 3 times 2. Okay. So if you do that, it will be n times n minus 1 times an times x to what power?
N minus 2.
N minus 2. Okay. All right. So we have two different ways of. This should be plus dot dot dot. We have two different ways of writing down the infinite series. The dot 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 notation, that's how I say it. So you can write it explicitly using dot dot dot, or you can use the sigma notation. The good thing about the sigma notation is it's compact. It's easy to write down than this one. Okay? And you also see that it's somewhat easier to find a pattern if you write in this format. However, sometimes the explicit meaning is lost. For example, you wouldn't know why this suddenly changed from n equals to 0 to n equals to 1 without thinking about the explicit form. Something like that could happen, right? So when you solve an equation where you have x's as coefficients, you have to be able to go back and forth freely. Okay? If you just know one side of the story, you can't really follow the logic. Okay? To fully follow the computation, you have to be able to go back and forth. Right? So keeping that in mind, let's plug everything in there. Oh, but before that, this is what I suggest for any solution using power series. If you have multiple terms as coefficients, you want to distribute them out before you plug it. So I'm going to rewrite this one as y double prime minus x squared y double prime minus 2x y prime plus 6y equal to 0. Okay. And then, since we have all the derivatives, let's plug them one by one. So this goes in here, so that'd be summation. So this would be summation. N starts from 2 to infinity, n minus 1, a n x to the n minus 2, minus x squared, summation n equals to 2 to infinity, n minus 1, a n x to the n minus 2, minus 2x, summation n starting from 1 through infinity of n times a n x to the n minus 1, plus 6 times summation of a n x to the n, and from 0 to infinity equal to 0. So this is what you get. Any questions so far? Just looks complicated. It's a very straightforward calculation if you think about it. Okay? So the key to understanding this part of the lecture is don't be scared. Okay? If you're not scared and you can just see what it is, then it's easy to follow. Right? Okay. So the next thing I can do is, this is a bunch of summations, just a bunch of things that are added, right? That's what this is. And there's a multiplication by x squared. Let's even put the minus in there. Okay. Then you have the distributed property, right? What's that? You can multiply to each individual ones, right? And then what that means is that what used to be the sigma of these will now be sigma of negative x squared multiplied to everything that's in there. Okay? What I'm trying to say is that you can bring this inside. Okay. If you accept that, then we can just now rewrite the equation in the following way.
So you assume that y is a polynomial function, right?
Yeah, you're assuming that y is an infinite series. Now remember, we still know that even for coefficients that change, solution will be unique for if you give the two initial conditions. Okay? If you provide y of 0 and y prime of 0, the solution is unique. So if we find something that works, it works. Okay? So the goal is to find the solution of this one that has two free parameters. Then we found the solution. Now, we'll see later in the Bessel function case that that's not always true. The Bessel function has a problem that this coefficient disappears at y of 0. When x is 0, this briefly disappears. So there's a jump. So something like that happens. Okay? But in this case, it's completely okay to assume that your solution is an infinite series. Right? Okay, so continuing on, n from 2 to infinity of, okay, so you have negative 1 times n minus 1, an. The thing is, x squared multiplied with x to the n minus 2, they have the same base, so the exponents add up, so you get x to what power? Nth power, right? Okay, and then plus summation n equals to 1 through infinity. Negative 2 is multiplied inside, you have n a n, and this time this is x to the first power. When you multiply to this, what do you get? X to the nth power. Is that okay? Right. And then plus 6 can be moved inside. You have 6an x to the n. N starts from 0 to infinity equals to 0. Okay. So that's our next level. And if you were told that you're looking for a solution that looks like a power series, really, until this part, anyone would be able to do it, as long as you're not scared. Okay? You can just do this much. There's nothing, no surprises going on. But here's where an important skill has to be learned. So I'll talk about two skills that's needed to solve an equation in terms of power series. One is that you need something called a shifting. That's the first skill. Yes?
So can we change the n value that starts so we can put them together?
Yeah, that's the idea. See,
Yeah.
you have x to the n, x to the n, x to the n,
We can
and
start from n equals to 0. Yeah.
yeah, that's exactly what we're doing. But let me just explain something. See, if you have some coefficient a0 plus, so if you have something plus something x squared x plus something x squared plus something x cubed plus da 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 equals to 0, it's a basic fact about Taylor series that if this is true in an interval containing 0, then all of these coefficients must be 0. Now, why is that true? Well, you just think about the Taylor series of 0. What's the Taylor series of 0? Just 0 for everything, right? And you're saying that the two sides are equal, not for a specific value of x, but they're equal for infinitely many values of x inside an interval. Okay? If that's true, then the only way that could be possible is each of these are equal to 0. So we're going to be using this as the reason for figuring out the relationship between the coefficients a,n's. But in order to do that, we have to organize everything here in the powers of x, right? So we want to put these sigmas together into single sigma with the same x power. But to do that, these are okay, but this is not okay. This is the problem child, right? We have to do something about this, right? Okay. So, and as some of you know, pointed out, you really want to change where the n starts, okay? And the way you do it is called shifting. And what you do is, you look at this n minus 2 and think about what you want. You want this n minus 2 to be n, right? And you replace this n by n plus an integer, or n minus an integer, okay? So that they're equal. So if you replace n by n plus 2, think about what happens here. If n is replaced by n plus 2, then what's n plus 2 minus 2? It's just n, right? So that's what we want. This is the shifting we want, okay? But you still have to think about what it means for this series. Well, what it means for this series is that every n that you see must be changed according to this thing that you have determined, okay? Once you determine what should be the prescription, you apply to everything inside your sigma, okay? Even this one, okay? So let's see what that does. So this portion, I should have brought a colored chalk today, but this portion right here is going to change to summation n plus 2 equals to 2 to infinity. n plus 2, n plus 2 minus 1, a n plus 2, x to the n plus 2 minus 2. See, I've changed every n that appeared here by n plus 2. Okay. But then we have to simplify this. So how does this simplify? Well, it's the same thing as, well, if n plus 2 equals to 2, then n is equal to what? 0. So n starts from 0. Okay. N starts from 0 to infinity. N plus 2. N plus 2 minus 1 is? N plus 1. And a n plus 2, and x to the nth power. Exactly as we wanted, okay? And that's called shifting. Now, why does shifting work? Well, you have to spend some time to check this, okay? If you plug in 2 into here, you get 2 times 1 times a to x to the 0th power. If you plug in 0 here, what do you get? 0 plus 2 times 0 plus 1, a of 2 x to the 0th power. You get the exact same thing. Plugging in 2 into this expression is the same thing as plugging in 0 to this expression. Plugging in 1 to this expression is exactly the same. Plugging in 3 into this expression is exactly the same thing as plugging in 1 into this expression. And it goes on and on, right? So you can see that this series, if you write them explicitly, you get the same thing as you would get if you write this one explicitly. As I said, being able to solve this requires you to be able to go back and forth between the explicit ... notation and this cryptic notation, the compact sigma notation. So if you go back and forth, then it will be very natural. So if you didn't fully understand why the shifting works, just sit down and just compare the terms one by one. You'll see that they're exactly the same. So these are indeed the same thing. Okay. All right, so now let's rewrite the equation with that thing changed, n from 0 to infinity, n plus 2, n minus 1, a n plus 2, x to the n plus summation n equals to 0 to infinity, no, 2 to infinity, negative 1, n minus 1, a n x to the nth power, okay, and then plus summation n equals to 1 through infinity, negative 2, n a n x to the nth power, plus summation n from 0 to infinity, 6 a n x to the n equals to 0. Okay. Now the second skill that you have to know is splitting off terms. That's the second skill. But let's think about what this is doing. You see, these summations, what do? They produce terms, right? That's their job. Okay. So suppose you got hired in one of these factories. What do? You make these terms. Okay. All day long, you do that. Okay. But if you go back and see what it's doing, you have 4 factories that are producing terms of the series. Their starting times are different. Okay. So let's say n equals to 0 is at noon. So at noon, the workers are in this factory and this factory, right? Yeah. They produce the very first some shiny-looking terms. Okay. I don't know if you can call it term shiny, but let's say if something generated here, something generated there, right? Okay. And then at 1 p.m., what happens? People start working on this factory, right? So these 3 factories are producing something at 1 p.m., right? Okay? But then this is still not functional. Okay? When do they start working? 2 p.m., right? At 2 p.m., all of them start working. Okay? And then what's going to happen is that nobody's allowed to go home, right? They're working until time infinity, right? Yeah. So that's the 4 factories that's working. Okay. So when you try to put all these 4 different factories combine them into a single factory, you realize that there's a discrepancy between their starting times, okay? These start the earliest, this one starts at 1 p.m. and this starts the latest, okay? So what you want to do is you want to combine the factories by saying that, oh, let's write down what happens at time t equals to 0, or n equals to 0, as a separate term. And also, what happens when n is equal to 1, as another separate term. And then, let's write the remaining one as a summation. Okay, so what I'm trying to say is that I want to write down n equals to 0 through infinity, n plus 2, n plus 1.
Yep.
N plus 1. Okay, and then a n plus 2, x to the n, as when n is 0, let's see what it produces. It's 2 times 1 times a2 of x to the 0th power. So it's 2, 1, a2, and x to the 0th power is just 1, right? So that's what it produces. Plus, okay, when n is 1, what does it produce? Tell me. So at 1 p.m., what does this become?
6.
Okay, yeah, you don't want to write 6. You want to say 3
3 times 3.
times 2. Oh, well, okay, maybe it's a specific case, so I guess that's okay. So 6a, 3, x to what power?
1.
1. So it's just that, okay? And then you write down the signal notation as before, but now your clock starts at 2, not at 0, because n equals to 0, n equals to 1, those two terms are split off. Okay? Yeah. So that's the second skill, okay? Being able to split off the first few terms so that now you have a single clock that keeps track of the time for all the factories. Yes?
You don't want to make it start all of them start from 2?
Yeah, that's what you want. Yeah, this one should split off the one n equals to 1. This one should split
I
off
thought
n
we can
equals to
just
0.
rewrite it n from 0 because because that is the roots of this. If you rewrite it such as the third term, we just write it n equals to 0, start from 0. So if we plug in there is
Okay. all right. So what's being discussed right now is, yeah, that's an interesting point. So if you plug in 0 to this one, you get 0 anyways, right? If you plug in 1, it's 0 anyway. So you can. It doesn't hurt to write down this to start at n equals to 0 and n equals to 0. Actually, that's another good point. So you could have done that, but what I'm trying to show is a method that works in general. It's
okay.
so when you go to something called Frobenius method, that doesn't happen always. So in that case, you have to do something like this. Okay. Yeah. Good point. Yeah. All right. So you have n equals to 2 to infinity of the same thing, n plus 2, n plus 1, a n plus 2, x to the n. Nothing changed other than n starts from 2. Okay? All right. So now, let's see what happens. Okay, if you split off the terms that correspond to n equals to 0, so for n equals to 0, there's something coming from here and there's something coming from here. What are those? So we already know that one. It's 2a2 plus, okay, so that's 2a2, that's 2a2. When n is 0 here, what do you get? 6a 0. And x to the 0th power is 1, so you don't write that. Okay, so you get 6a0. Okay, and as I said, you want to put the same powers of x together. Okay, so that's the constant term. Okay. This 2a2 was the one that's produced by here at n equals to 0, and 6a0 was the one that was produced by here when n is 0. Okay, plus when n is 1, you have 6a3 And I want to factor the x out. So I'm not going to write the x for now. It's factored out. Okay, so this one is yet to produce anything, so we skip that one. N equals to 1. What does this become? When n is 1, what is that?
Negative 2 a1 x.
Negative 2,
a1.
1 times a1, and times x, right? Okay. Plus, okay, what about this one? When n is 1?
6 a1 x1.
Yeah.
X.
6a1. All of them having x to the power of first term. Okay? Is that okay? All right. And then once you do that, now the clock starts from 2. Then the remaining thing can be all combined into a single clock. The factory workers don't have to work with 4 separate clocks. They can just use one clock to start at 2. Okay? It's just that some workers have to show up earlier to reuse some things. Okay? But after time 2, after n equals to 2 and infinity, all of them are going to produce, well, be rather big, so let me write like this parenthesis, to the x to the nth power. Okay? Where this one, if you factor the x to the nth power out, this is what you get. N plus 2, n plus 1, a n plus 2, and then plus negative 1 n minus 1, a n. Notice that I'm not writing x to the nth power because I'm trying to factor it out, okay? Then plus negative 2 n times a n plus, what's the last one? 6 a n, right? So that's it. That's equal to 0. Okay, take a good look at it because I'm going to erase it again. Yeah. I'm trying to fit everything inside this one camera, but you know, when I'm not recording and I'm solving this, I usually go all around the classroom just to solve one question. I would start from here and then I would use all the blackboards, and by the time I go like fully to the other side, then the problem solved. Okay. So yeah, we've come a long way, right? But there's still more to be written. Yeah, remember, we've done a lot of things, but you just have to remember 2 things. What are those 2 skills? One is shifting, the other one is splitting off terms. Okay, if you know those 2 skills, then you can do this on your own. It's not too good. Okay. All right. So now what we do is, since I've organized everything in terms of power of x, for this to be equal to 0 as functions. Remember, when we solve differential equations, the equality is not equality for some x, it's for all x, okay? Yeah, or at least equal to, the 2 sides have to be equal for infinitely many values of x inside one interval, okay? That's what it means. And that's a stronger condition. That forces each of these coefficients to be 0, right? So here's what we have. We have that 2a2 plus 6a0 to be 0. And also 6a3 plus, actually, minus 2a1 plus 6a1 to be 0. And also n plus 2, n plus 1, a n plus 2, minus n minus 1, a1, minus 2n a n, plus 6an has to equal to 0. Okay, so those are the conditions that we have. And notably, this last one is not a single condition, but actually for all n2 or greater, right? So keep that in mind, because this is not a single term, but infinitely many terms. This last equation gives you infinitely many conditions for n2 or greater. And that's our goal to solve. Now at this point, it's a bit confusing what you're trying to solve for, so let me give you some idea. I said that such an equation, if y of 0 is provided, let's say y0, and let's say y prime of 1, y prime of 0 is provided, let's call that y prime 0. Okay. Hopefully that notation doesn't confuse you. So this is a number, that's a number, okay? Now, if your y is a0 plus a1x plus a2x squared, just like that, what's y of 0?
A0.
A0, right? So this really, what I call it as y0 is really a0, right? It's really a0, right? What's y prime of 0?
A1.
If you differentiate, this goes away, this becomes a1, and that's 2a2x, and if you plug in 0, you just get a1, right? So, as I said, if you provide the values of y0 and y prime of 0 for this equation, we know that the solution is unique. That's called Peano's theorem or something. So you're going to treat a0 and a1 as some given values, right? Although it's not given to you, we're going to treat that a0 and a1 are the given values, and everything else has to be solved in terms of a0 or a1. Now, why do we want it that way? We want it that way because then at the end of the day, the solution will only have a0 and a1, right? That's two free variables. And that's exactly what we want. A second order differential equation should only have your solution as two free parameters. Okay? If you have more than that, something's amiss, right? If you have less than that, then you didn't find all the solutions, okay? So you need exactly two. That's why you want to solve everything for a0 and a1, okay? So let's do that, which in the first two cases is easy, right? What is a2 then? a2 is negative a3 a0, right? Okay, here a3 is negative, or 4 divided by 6 is negative 2/3 a1. Am I right? You're
Yeah.
following?
Yeah.
Okay, good. Yeah. All right. Please check my calculations. All right. Okay. And then now we have to solve for this, but notice that because we're trying to have everything expressed in terms of a0 and a1, you always solve the higher index by the lower index, right? Do you agree? Right. So what you want to do with this is you want to solve this, it should be an. You want to solve this in terms of an plus 2. You want this to be a function of something times an. Is that good? All right, so let's do that. So n plus 2, n plus 1, an plus 2. See, if you put a minus here and multiply this out, that's n squared minus n plus 2n minus 6 an equal to 0. Okay. See what I did? I factored the minus out and also the an's out because they're all here, right? And then you have n plus 2, n plus 1, an plus 2. It's n squared plus n minus 6. How does that factor?
Is n plus
n
3,
plus 3,
n minus 2.
n minus 2. Thank you. an. 0. So now you can move this to the other side and divide by n plus 2, n plus 1 to get an plus 2 equal to n plus 3, n minus 2 over n plus 2, n plus 1, an. Okay. And this is valid for n greater or equal to 2. Now this is a very important result in our solution because, see, knowing A0 and A1, let's pretend that we are given A0 and A1. Then we know what A2 and A3 are, right? But then if you know A2 for n equals to 2, this tells you what? A? 4. A4 will be something times A2. Is that good? And if you know A3, this equation will give you A5. And so on and so on. You can just reuse this for n equals to 2, 3, 4, 5, 6 to infinity to find all the values of an.
Why is from 2?
Oh, because this equation came from n greater or equal to 2. This summation starts from n equals to 2.
Okay.
Yeah, this implies that one, which gives you this one.
And since we also already know the value of A0, A1, A2, and A3.
Say that again? What did you say?
Since we already know the value for A0, A1, A2, A3, right?
Yeah, if we know the A0 and A1, then we know A2 and A3, and then this, if you apply it again and again, you know A4, 5, 6, 7, all that, okay? And because you're using this again and again and again, this has a name. It's called a recurrence relation. And in my exams, I always ask everyone to write down the recurrence relation, the circle of the recurrence relation, because knowing that is a significant achievement in a power series solution, right? And when you write down recurrence relation, you must write down starting from when it's valid. Okay, sometimes then it will start from 1, sometimes it's going to start from 2 or 3, who knows, right? And you have to write that down, right?
Do you mean recursive?
You can say recursive relation or recurrence relation. Yeah, it's a recursive formula. Okay, so let's continue on. So let's see what A4 is then. A4 is, we plug in n equals to 2, right? So it's 5 times, 0 over 4 times 3, A2. So what's that? A4 is? 0. So A4 is 0, right? Is that okay? A4 is 0. But then the next number, if you use A4, if you plug in 4 for n, what does that give you?
6.
A6. So you get A6 equals to some crazy number here times A4. What's that equal to?
0.
0. Okay. So you can kind of see what's going to happen. What do we know now?
Even terms.
A even numbers, so A2n, let's say 2m, with m 2 or greater would be 0, right? So that's one result that we get immediately. And that's a feature of the Legendre equation. The Legendre equation has, L times L plus 1 times y. And sometimes the even ones will be 0 for L even. And when L is odd, then after some point, some odd numbers, odd indices of A's will be 0. Okay, so the conclusion is that there will always be a solution of the Legendre differential equation which terminates, and that gives you a polynomial solution. So one thing that you will see in general if you solve for other L values is that this equation will always have a polynomial solution, and those polynomials have a name. They're called Legendre polynomials. Right? And you normalize those with some certain values. So that's what you do. Right? Okay, so that's one result. Let's just write that down somewhere here. A2m equals to 0, and 2 over here. Okay, now let's carry on with A5. Okay, A5 is with n equals to 3, right? So that's 6 times 3 over 5 times 4 of A.
Is this
That'd
3?
be one.
It's 1, I think. N is
Oh, yes.
3, right?
6 times 1. Thank you. Yeah. Right. And A 3, right?
Yep.
So N is 3. 3 minus 2 would be 1.
Yep.
3 plus 3. Okay. All right. So you get that, which is, if you rewrite this, it's
3 over
6 times 2 times 1 over 5 times 4 times 3 with a minus, right? A1. Okay, so I'm just sticking in this 2 and 3 down here. And I like this format because it's 5, 4, 3, right? Okay. Let's write down what A7 is. A7 is 8 times 3 over, what is it, 7 times 5? The same times 6, right? Is it okay? Times 6 of A what? A 5. So what's that? That's still negative. So negative, it's 8 times 6 times, I just want to write in order. Maybe that's not what I should do. Oh, you know what? I should multiply this with this. Okay, so we have 8 times 6 and 3 times 3 times 1. Sorry. 7 times 6 times 5 times 4 times 3. And then I'm missing a 2 here, right? Okay, is that okay?
Where the 2? Oh, yeah.
Yeah, so, no, is that right? 2? Right, so 8, 3, 8, 3, and then 6, 1, 6, 1, and there's a 2 I'm going to split off. Okay. All right, so I like this because now I see a pattern in the denominator. What's happening?
It's
Factor-
NCR.
It's almost like factorial, right? So something like that. So if I had a 2 times 1 and multiply by 2 times 1, then this will be a factorial, right? So let's write it like that. What's that? 7 has 7 factorial. 5 has 5 factorial. Okay? And 3 would probably have 3 factorial, which is true, right? 3 factorial, right? If you attach the 2 and 1, right? So it would be negative 7 factorial. And another idea is to take this one and factor a 2 out. So it's 2 squared times 4 times 3, right? And then 3 times 1. And 4a1. And let's do the same thing here. 2, write it here, 4a1. Now let's do another one, A9. A9 would be 10 times, n is 7, right? To get 9, you get 7. 7 minus 2 is 5. 10 times 5 over
9.
9 times 8 of A7, right?
Yep.
Well, A7 is this much, so this will be negative, rewrite 10 as 2 times 5, so that now it's 2 cubed, 5 times 4 times 3, right? And then, now it's 5 times 3 times 1, over 9 times 8 times 7 factorial. What's that? The denominator is multiplying. What's that? 9 times 8 times 7 factorial?
Factorial.
9 factorial of 4a1. Okay, so I think I now have a generic formula for the odd ones. I think I know the generic formula for the odd ones. it looks like if n is odd, here's what I'm getting. It's like a n would be, so you can pull one of the 2's out and attach it here so that it looks like factorial, okay? So you have here 4 factorial and then 5 factorial. So as n increases, this one factorial goes up, right? So what you get is negative 2 squared 2. This also increases. So it's like if I put this as first power and then 2, 1, 2, 3, 4, 5.
N minus.
So it's n minus 6, right? N minus 6.
Is it? No, I think it's not. Because
No. Sorry. Oh yeah, I'm calling this as n, so it's okay. If this is n, relation is 2 to the n minus 6. Okay? And then you have n minus
I think it's
4 factorial.
Because
The n here and this n is different. If you don't like, we can use n plus 2. Is that what you're saying?
no, because the difference in A7 and A9 is different because that is A7 is 2 to the 1 and A9 is 2 to the 2. The difference is
Oh, you're right.
from
right,
6
right,
to
right.
7.
7 to 1 is minus 6. 9 to 2 is
Minus 7.
minus 7. Okay. So, I didn't want to do this, but I guess I'll have to. Okay. How do you write down an odd number in general? So you write down 2m for even numbers, right? 2m is an even number. How do you write a generic odd number?
2n plus 1, 2n minus 1.
Yeah, because if you have an even number, adding a 1 or subtracting 1 will give you an odd number, okay? What's an odd number? It's a number that's 1 more or 1 less than an even number, okay? So you can say that for n equals to 2n plus 1, okay? See what I'm doing here? n equals to 2n plus 1, so that's a generic odd number. So a 2n plus 1 is going to have, well, let's see, what's m here then? 7 equals to 2n plus 1. M is 3. So this is m equals to 3. What's m here?
4.
4 times 2 plus 1 gives you 9, right? So that's m equals to 4. So 4 gives you 2, 3 gives you 1. What's that? What's the relationship now? Minus 2, right? So it's 2 to the m minus, so it's always minus, 2 to the m minus 2. Okay? And then you have 7 is 4, 7 minus 3 is 4, 9 minus, right, oh, no. 3 plus 1 is 4, 4 plus 1 is 5, okay? So you see that this is m plus 1 factorial. Is that okay?
Yeah.
All right, and then, now, this one seems to be increasing by 2's, right? So the next one will be 7. So this one's not related to m, but this number here. It's always 4 less than this. And another thing is it's multiplied times, it's decreasing by 2, right? So there's a separate notation called a double factorial. So if you have like 5 double factorial, that means it's 5 times 3 times 1. And like 7 double factorial will be 7 times 5 times 3 times 1. Okay? So that's another notation people use to talk about what's happening here. So what happens is that it will be 9 minus 4 gives you 5, 7 minus 4 gives you 3. Right? So it's going to be 2n plus 1 minus 4 double factorial. Okay. Will be that one. And then the bottom one will be exactly the same as this factorial, right? So it will be 2n plus 1 factorial. And then you have 2 squared a1. Oh, there's a 2 squared and 2n minus 2. So that's perfect, because now that will be negative 2 to the nth power, m plus 1 factorial, 2m minus 3 double factorial over 2m plus 1 factorial of a1. All right, so that's what we have. Okay. Now, at this point, some of you might be freaking out because how am I ever going to do this on the exam? Well, for my exams, I don't ask you to find the general formula. I'm just doing this because we need it for the later course. What I usually ask during the exam would be, I would ask something like, find the first 4 non-zero terms or 5 non-zero terms, something like that, okay? And you just have to figure out, so what's 5 non-zero terms? That's A0, A1, A2, A3, A4 is 0, so you need A5, right? So if you have those values, then those become the answers. Okay? So it will be much easier in the exams, okay? So don't freak out, but I'm just trying to tell you that this will be the general formula if you track all the odd terms, right? Okay, so we're almost there. Okay, so let's now write down what y is. Y is A0. A0 is A0. A1 is A1. Those are the two given values. That's how we were thinking of it, right? But then A2 is what? A2 is minus 3A0 x squared, right? Is that good? Okay. And then A3 is, let me see, does this one fit in here? Let's see, if you plug in, what's m for A3?
1.
1. Okay, so if you plug in 1, 2 to the first power, 2 factorial, oh, that gives you a minus, so it's a bit hard to say. Okay, so we can't use that. We'll just have to write that separately. So A3 is negative 2 over 3 A1 x cubed, okay? But then starting from m equals to 2 and above, right? The values are these, okay? And it's a summation, so it's a summation for m equals to 2 to infinity. With I pulled the negative sign in front, so I just have to write everything down without the negative sign. So you have 2 to the m plus 1 factorial, 2m minus 3, double factorial over 2m plus 1 factorial, a1. Okay, x to what power?
2m plus 1.
2m plus 1. Because this much here, well, with the minus sign is a 2m plus 1. That's the one that's attached to x to 2m plus 1, right? So that's what you have as a generic solution. And again, if the question was to find the first 4 non-zero terms, what's your answer? It's this plus this plus this plus this, and you stop. Okay? So it's much easier, right? Okay. Yeah. Okay. Now, however, I also want to rewrite this in a different format so that it's clear that you have 2 free parameters. And the way you do it is by first factoring the a0 out, and you write down a0 times 1 minus 3x squared. And then the remaining terms of a1 as a factor, right? So I can factor out the a1. And if you factor the a1 out, it's x minus 2/3 x cubed plus minus summation of m equals to 2 to infinity of 2 to the m plus 1 factorial, 2m minus 3, double factorial, over 2m plus 1 factorial, x to the 2m plus 1 And notice that A1's gone because I factored it out. Okay? So what are we getting here? I have two free parameters, A0 and A1. Right? And that gives you two functions. So this is a function by itself. So if you set A0 as 1 and A1 as 0, this by itself will satisfy this equation, right? So writing it this way, you know that 1 minus 3x squared is a solution to this equation. I mean, who would have known that unless somebody tried it like that, right? It's really hard for somebody to say, hey, this has a polynomial solution, unless you do it the series way, okay? But if you do it the series way, you will find that this is a solution, right? You have a polynomial solution. And then there's this another solution, okay, which is an odd function. By the way, this is an even function. That's an odd function because it only has odd powers, right? It's some power series. I don't know what that is. It's some strange function, okay? But it's that function times A1. So you have an infinite series as one solution, and you have a polynomial as a solution for a Legendre differential equation. And that's what I mean by saying that for different integers of L, you always have a polynomial solution and another power series solution. Okay? And often what happens is that these will have, it has a finite convergence. You know, in calculus 2 or 3, you learned the interval convergence, right? So this doesn't converge for big values of x. I think it only converges between -1 and 1 or 0 to 1, something like that, okay? Oh, from -1 to 1 it converges. But when you get to 1 or -1, you run into problems, and that makes this violate some physical conditions when you try to use this for solution of the Laplace or wave equation in ball. So eventually what you do is you have this Legendre equation for PDEs later. You have a polynomial solution and some other function, but that solution is invalid. It doesn't satisfy some physical condition at 1 or -1. We throw that away and you just have a simple polynomial as your solution. So that's what's going to happen later. Yes?